Welcome everyone to another session for learning at Lambert Labs, and today's presenter is Millie, so I shall hand over to Millie.
Thank you, Aaron. I'm Millie, and I'm going to be talking about general purpose GPU programming using OpenCL. So we're talking about general purpose GPU programming, but maybe we should start with what GPUs are usually used for. So traditionally, graphics cards are used for graphics programming. This is a task of taking a set of primitives in 3D space, usually triangles, and rendering a picture to the screen that the user can see and understand. So this can take place in real time. For example, if you're making an interactive application, such as a video game, the user needs to put an input and it changes the scene somehow. It can also be pre-rendered, which would be more like a CGI film or something like that. But in either of these applications, there's an incredibly large amount of computation you need to do very quickly, which means you need specialized hardware. And this is what GPUs were made for, to do a very special purpose thing. Because to achieve that sort of performance, you need to restrict what types of work you're doing quite a lot. So it's usually just like operations on floating points and vectors of floating points. So what is general purpose GPU programming? So general purpose GPU programming is when you use the graphics card for any task that isn't graphics. And this is usually going to be some sort of function that's very expensive to execute. And for whatever reason in your application, you need to make it go fast. So the tasks that okay, I've mentioned that it's a special purpose piece of hardware, the GPU. So only tasks which fit into that special purpose are well suited. So these are mostly going to be tasks that are quite similar to graphics. So an example of that would be computer vision, which is sort of the reverse operation of computer graphics. Then something else would be like the training of neural networks. Particularly if it's like a neural network that operates on images, it will be quite good to put it on the GPU for increased performance. And the elephant in the room here is Bitcoin mining. This is probably the most common application of general purpose GPU programming. It's incredibly environmentally destructive. I found online that Bitcoin has a similar carbon footprint per year to New Zealand at 37 million tons of carbon dioxide, but it remains the main application of GPU programming at the moment, which is a bit crazy, but there we go. So why are we using OpenCL to program on the GPU? So most frameworks you're going to find for GPU programming are vendor specific. So for example, NVIDIA has one called CUDA, and that only runs on NVIDIA graphics cards. And that's quite good because like NVIDIA has lots of optimizations for their own graphics card that make it go super fast on their chips, but it also restricts you to being stuck using NVIDIA hardware. So OpenCL is an API that sits on top of all these vendor specific ones, and it's implemented by all the different vendors to provide a common interface. And this is good because you can still get the vendor specific optimizations, but your code still runs on different platforms. Also, as a fallback option, you can just execute it on the CPU in a thread pool. So even in the worst case, you could still get, if there isn't a GPU available, you could still get some performance improvement. Being platform independent isn't always super necessary. So if you knew you were going to be on NVIDIA hardware, maybe it would be better to go for CUDA, but being platform independent is always nice. Okay, so I've mentioned that GPUs are special purpose hardware. They can be quite temperamental. And if you want to get the most out of them, there's quite a few restrictions on the sort of task you that are going to make the most out of the GPU. So I've written down a couple of like good features of a task that make it good for GPU optimization. The first one is that it's got to be composed of lots and lots of subtasks. And this is because like the task is like parallelized on the GPU. There's lots and lots of different threads running at the same time. So you have to be able to divide up your job into lots of little pieces that can be run in different threads. So for example, if you were training a neural network, the task would be the evaluation at each node. So maybe you calculate the error function at each node of the neural network, and each one of those nodes is a different subtask for your overall operation of training a network. Another restriction you might make is that these tasks or these subtasks have to be very similar in shape and basically almost identical. So we're going to get a bit into the underlying architecture here. So yeah, so to run a very large amount of threads, what's going to happen is they're going to be divided up into little chunks of threads, basically. And these chunks are called work groups, and they contain maybe 1,000 threads in one block. And they're executed in blocks. So within one of these blocks, all the threads have to be doing very similar things. They can't really diverge in behavior. It's a bit like simultaneous instruction, multiple data optimizations, if you know about that. So basically on the CPU, if we had multiple threads, you can have your different threads doing whatever you want, okay? One can be pinging a server, one can be writing to a database, one can be reading from the hard disk. But if you're on the GPU and you're within a work group, they have to be doing basically the same thing. So if we take a very simple example, like an if-else statement, and let's say these two threads diverge on which branch they take in the if-else statement. So what's going to happen is that the first thread is going to do its work, but meanwhile, because the second thread isn't allowed to really be doing anything else, it's forced to just go to sleep. It's sort of paralyzed for a bit because it can't do something too different from what other threads are doing. And then the same happens in the other branch. So in the else statement, the first thread goes to sleep and the second thread does its work. And this is a bit counterintuitive because it means that on the GPU, most of the time, it takes the same amount of time to execute both branches of an if-else statement as it does to execute one. So you can see that the more the different threads diverge from what each other are doing, the worse this performance is going to get. And eventually you may erase all your improvements, and it may actually be faster to run it on the CPU after all this work. And that's a shame because like it is hard to get stuff running on the GPU, and you need to make sure it's worth it. So it's very good to have all your subtasks being very, very similar in what they're doing. Okay, and then I guess the third requirement is that these tasks need to be very independent of each other with regard to synchronization. So I mentioned these things called work groups, which are like collections of threads. So across work groups, there is no synchronization. So if you've got one thread in one work group and one thread in another work group, there's no synchronization between them at all. And this is because these work groups are like pipelined and they're running queues. So by the time one work group executes, another one might already have finished. So there's no reason to synchronize between them really. So if you're within a work group, there is some synchronization, but there aren't any locks, there aren't any condition variables. There are atomic data structures, but they're kind of slow, and you don't really want to use them. The main way of synchronization is going to be this function called barrier. And what the barrier function does is it says, by the time a thread reaches this function, all other threads also have to reach it before it can go past. So think of it like a checkpoint. All the threads have to reach this checkpoint by anyone before any of them are allowed to go past it. And this is also not super performant, but what you're going to do is you're going to put a barrier function at quite critical points in your code to make sure all your threads are synced up just at the right time. So in between major operations, basically. Okay, so let's have a look at what a GPU program looks like. So this is very similar to C, as you can probably tell. I'm going to go through it line by line, just to explain everything. So the first word is the kernel keyword, and this basically says that this is your main function, right? This is your entry point. This is where your function starts, because this function is going to be called a lot of times, right? Because when you set off your job, you're going to say execute this function 1,000 times or something like that. So this is your entry point. This is the function that's called 1,000 times in parallel. And that's what the kernel keyword denotes. And it also shows that this function is going to be visible from the CPU. So you can call this function from your C code. The next line is, so now we're into the parameters of the function. We've got an input array of floating points. That's, if you don't know C, that's what this star means, that is an array. And the global keyword is going to be a bit like the kernel keyword in that it says that this array is visible from the CPU. Because, yeah, I mean, to put it in perspective, like we are on the CPU running our code, but we're calling code on the GPU. So we're calling code that's on a different chip. So we need to say that this data is visible from the CPU. And then there's also a similar one for output. So there's two arrays of floating point numbers, an input one and an output one. And then our third parameter is the number of elements in the array. That's just because in C, you don't know the length of an array. So you have to supply it as well as a third parameter. So then we get into the body of the function. And the first thing you need to do is, because this function is called like 1,000 times, you need to know which of those 1,000 threads you are, okay? So this function get global ID is going to tell you which of the threads you are. And then in this if statement, we do a quick sanity check. We make sure we're not going out of bounds on our memory. And then finally, we actually do this operation. And here we're going to be doing the square. So we take each element of the input array and we square it, multiply it by itself, and we put it in the output array. Okay, so I appreciate this is a bit complicated, so I might come back, like we can do some questions and I'll explain some of it. So let's run this. Let's see how it works. For like a benchmarking thing, I'm going to do it in Python first. Then I'm going to do it in Python using multiprocessing, the like parallelism library in Python. And then I'm going to use OpenCL. And for our test program, we're going to be calculating the first 1,000,000 square numbers. Okay. Okay, so I've got this Python. This should be a bit more familiar to everyone, hopefully. I've got a Python script, and it basically has an array of length 1,000,000. This is like the input array, I guess, in the OpenCL example, and it iterates through this array and squares every number. So it's quite simple. And then it takes the time to check how long it took. So if I run this, we will see. Oh yeah. So it takes 0.13 seconds, 130 milliseconds to calculate the first 1,000,000 squares in Python, like naively. So now we're going to go into the next one, which is the multiprocessing library. I'll step through this one as well. So we have our function square. This is a bit like the kernel function in the OpenCL, which, let me go back. It's analogous to this function here, is our squaring function here. And what we're going to do is so we're going to import the multiprocessing library. We're going to create a thread pool of size 5, or a process pool, I should say. And then we're going to map this function over 1,000,000 numbers. So we have a thread pool of size 5. We would expect, and actually, if we look at my Mac, it's running on 6 cores. So maybe we would expect a speed up of about 5 times, maybe. That would make sense if we're running 5 threads in parallel. But actually, it's going to be slightly slower. And this is because of this is because of the overhead of making lots of processes, basically. Maybe if we had a more expensive function, like the overhead of creating processes would be less compared to the actual work, and it would work out. But in this case, I mean, it shows you why Python isn't well suited to this sort of thing, because you run it 5 times in parallel and it actually runs slower. And this will give you an idea of how these sorts of things can be quite finicky, and just putting it in parallel doesn't always guarantee it to run faster. I mean, maybe we can talk a bit more about exactly why this happened at the end. But I was quite surprised when I wrote this script and it came out that way. So finally, we're going to do the OpenCL example. So actually, I should mention that there is a Python wrapper for OpenCL, but I only found out about that after I got this example. So we can do this we can use OpenCL straight from Python. But yeah, so here we see the function here, and this is the one that I just copied from the slides a second ago, and it's stored as a string in the program memory because it's C. It's just a bit easier to store it there. So this is our main function, and then there's going to be lots and lots of quite scary boilerplate. So I don't want to go too much into this because it's all about, you find the device because there may be multiple GPUs, you create a context, you create commands, there's loads of boilerplate that you have to do, but finally you can create a program and you can build it. It's compiled at runtime. And then finally, we are going to execute the kernel down here. So this is where it's actually executed. We wait for it to finish and we do our timing here. So if I run this, we're going to see that it takes 1 millisecond. Yeah, the timing isn't more precise than this, but you know, we've gone from taking about 160 milliseconds to taking about 1 millisecond. And that's about like, well, that's like a speed of like 100 times. So it's pretty significant, I think. And yeah, that can be like, I mean, 2 orders of magnitude can like make or break like a bottleneck in your code. So I think that makes the case like that if you have something that can be optimized easily using GPU programming, then it is definitely worth it. Okay, that's a demonstration. I appreciate I went through a lot of complicated stuff quite fast, but I was trying to fit it into 20 minutes. So if anyone has any questions, I can go over some of the complicated bits.
I have a question, Millie.
Yeah.
Not flicking back necessarily to like the complicated code, if you like, but it's more about, okay, if you had a team of developers working with GPUs, or, you know, trying to put together workflows that are dependent on GPUs, what would I guess the question really is that would you expect developers would you expect developers to have a local development environment where they can test stuff using a GPU, you know, in their local hardware, or would you expect the developers to be working on remote machines? What would be the traditional way of working there?
I think the best way of doing it is you make sure each developer has their own local GPU. I mean, this is the sort of thing that like Google Cloud does let you have access to GPUs in the cloud. So you can do it remotely like that. But I think that the normal way of doing it is you've got your desktop computer, it's got a fairly decent GPU in it, and you're working locally, basically.
And presumably using OpenCL then, flicking back to that negates against any problems caused by different developers having different GPUs. Is that correct? Or GPUs from different hardware producers?
Yeah, precisely. So you use OpenCL because it's agnostic to whether you're running on an NVIDIA GPU or an AMD one, or maybe you don't actually have a GPU at all. Maybe you're just running it on your CPU for now. But OpenCL is like a layer that abstracts over all of those.
Oh yeah, that's a good point. So you could just still run it on a CPU using OpenCL, like you mentioned. Okay.
Yeah, exactly.
I've got a question as well. Yeah. Talking about tasks and then splitting them into subtasks.
Yeah.
You know, is that would you expect developers to really, when they're designing an application that would use the GPU, would you expect developers to really think about how they design the tasks so it's split into subtasks in a really quite nice way, or is that something that OpenCL handles for you?
So really, this is like a very high level design decision that needs to be made, because if you can't, so the function you're going to be writing is this one. This is like the subtask function, if you think about it, and it's copied over all the different subtasks. So you can't hand OpenCL a task and say, split this up. You give it the subtask and you say, run this subtask 1,000,000 times. So you have to be very explicit, and you have to quite carefully design how you approach the problem to get the most out of the GPU.
Yeah, yeah, that does make sense. Does anybody else have any more questions for Millie?
Not from me.
Okay. Thanks, everyone. Thank you, Millie, for that presentation. And yeah, thanks for listening. Okay, I've halted recording.